And now on to our next section in the dry friction section. The next thing that we're going to talk about are square threaded screws. 8.8 square threaded screws. Right there. Now for the couple of you that have already taken engineering graphics, you remember that we talked about screws a little bit. We talked about the idea that square threaded screws are especially good for if you want to move a lot of force, right? The screws that we usually have to attach something to the wall or something, those are not square threaded. They have all kinds of different shapes that we looked at. But things like tools where we do heavy lifting, they usually include square threaded screws. And one that where you might have seen it, or two different places that you might have seen it, is if you have a chair, like for instance, like a piano chair or something, that you kind of have to kind of a little stool, and you turn it and the seat goes up or down, right? Then if you look down beneath, you'll see that's usually a square threaded screw in there. Also, if you need to change your tire and you use the tire jack to lift up the car, then you can see that, like, you know, your turning motion basically turns a square threaded screw. All right, but let's see if we can draw something that looks something like a square threaded screw. Let's draw the top. Be that. All right, so this could be any kind of top. Do some lines here so it looks a little bit like a hexagon there maybe. And then let's do, how are we going to draw this? Let's just draw the threads, and then we'll do the screw afterwards. So of course these are highly exaggerated. It wouldn't be that big of that thick. Oops. Something like that. And then my shaft of the screw would be something like that. Now an actual screw probably is going to have more than just 4 threads going around, but that's just to give us the idea. And now let's define a couple things. First thing we'll define is the radius of the screw. Right, that's the radius of the shaft. Call that lowercase r. Put it over here. We'll say r is the radius, not the diameter, the radius. And then we say the distance in the vertical direction from one thread to the next. Call that L. And L is what we call the screw lead. Right, so basically if I turn the screw once around, I'll move from here to there, right? If I go 360 around. So that's our screw lead. Then we will say the angle that is created between the thread and the horizontal. That's another theta. We're getting very used to theta at the moment. So theta is what we call the thread angle. Thread angle right there. And then if we want to tighten or loosen the screw, then we'll apply a moment. If you look down on the top, right, if you have your socket screwdriver or something like that, or if there's a slot in it, just a regular screwdriver, we call that M for moment. And then if we tighten that screw, so move it downward, then it will create a force. And that force we'll call F. Sometimes it's called W, but we'll call it F here. And that's the axial force of the screw. Axial force of the screw. And with that, we've defined everything that we need to do. Now, how does that relate to friction? Right, we're doing the friction section. Well, if we think about, right, if I'm not the screw itself, but I'm the nut or the piece of material that's being pushed into, right, then if I think about I'm a little block that's moving up and down along these inclined planes, and the friction between those is what's going to be interesting. So let's zoom in on that area there. Let's draw ourselves, let's try and draw that straight like that, right? So that'd be basically the inside, the top side of my thread here, that kind of section right there. And then I have my little red box here, and that little red box is sliding up along. And so we can say we have the forces acting on it. That's my force here. And I can say I have a force acting it from the side. That's the force that I get from that moment. So we can say P is equal to M over R, right? Because it's just the moment divided by the distance of the moment arm. And those are the two forces that are acting. And of course, this is a rough surface. So we'll say that this contact surface has some mu s. All right. Of course, just like with everything else, we'll do a free body diagram. That's our free body diagram. We know we have F coming down. We have P acting in this direction. Now we are moving, if we're tightening, right, tightening the system, then we're moving upward. So that means our friction force has to be pointing downward. That's the friction force, and of course the normal force is acting perpendicular to that. All right. For a free body diagram, we can do sum of forces. Now, what do we have? We want to find, well, I guess we want to find F in the end, because that's really what we're looking for. Or P. Well, if we have P, we have the moment, so if we want to create a certain force, we'll know what moment. So let's solve all this for P. If we want to have P, then we need to know what F and N are. So let's do sum of forces in the y direction. Let's do our little X, Y coordinate system. Let's see. Sum of forces in the y direction is equal to 0. Is equal to what? Well, we have minus F. We have the force here, the friction force, right? So that would be, my angle would be sitting in here. That's my theta, right? I know that this angle is theta. Maybe let's draw that in here. That's theta, so I know that would be theta. I'm looking at the vertical direction, that should be sine. Let's go downward, so minus. So minus F times sine theta. And then the n, the component of the n is pointing upward, and it's the cosine. Plus n times cosine theta. All right. Now I have too many unknowns in here. Let's say that we're gonna are at impending motion, of course. So we can add another equation. Impending motion. That means that at my little surface here, I know that F is equal to mu s times n. So I can plug that back into my equation up there. So I basically can say that 0 is minus F minus mu s times n times sine theta. That's that. And then n times cosine theta is minus F minus n times mu s times, nope, not cosine, but sine theta well, let's put this up plus and then do a minus here, because then we can leave that as a plus back here. Plus cosine theta, and it looks like that's gonna work. So let's see. Do I have the right directions here? I think I do. I think I have a mistake in the notes. Well, let's see how far we get here. So let's double check on the directions just to make sure. So my, where am I? My friction force is going downward, so it's negative. Negative, F is negative. My N is going upward, positive. Okay, so I have the right version here. And then we can solve this for N. So N is gonna be F divided by all of this. Cosine theta minus mu S sine theta. All right, now that we have N, we can go ahead and see how to get P, which we're looking for. All right, well, first I guess we can say we can get F as well, lowercase f, the friction force. All right, so that's just mu S times N. So that would be mu S times F divided by cosine theta minus mu S times sine theta. All right, so then we can go in the x direction. The x direction we have P and then the two components of the forces. So sum of forces in x equal to 0 is equal to, we said we have P acting to the right, so that'd be positive. And the other two were acting in the other direction. So F times, that'd be that component there, so that should be times cosine, and then the other one is sine. Cosine minus N times sine theta, which means plug in F and N. That would mean we have mu S times F times cosine theta over cosine theta minus mu S sine theta minus N was without the other one, so times sine theta divided by cosine theta minus mu S sine theta. All right, so we can then go ahead and solve that for P. So P is equal to all of this. I think what we're gonna do, we can probably combine these together. We can pull an F out of there, of course. And then that is mu S times cosine theta plus sine theta divided by cosine theta minus mu S sine theta. And now we're going to do a little math trick to get this all nice and simplified. We will expand by 1 over cosine. Which of course we can do. And that means we get F times mu S of cosine theta over cosine theta plus sine theta over cosine theta divided by cosine theta over cosine theta minus mu S times sine theta over cosine theta. Now you're going to say this looks even worse, but actually we can simplify a whole bunch there. So of course cosine about a cosine is just 1, so we'd have mu s plus sine over cosine is tangent theta divided by, that's again 1, minus mu s times again tangent theta. So that looks a little bit nicer. So that's a good start. And then next we can remember that we defined mu s to be tangent of phi s, right? So we can write this would be the same as tangent of phi s plus tangent of theta divided by 1 minus tangent phi s times tangent theta. Now this does not look all that great, but if you go back into a trigonometry book and look at all those different identities, then you will see that we can actually get an identity here. Simplifies quite nicely because that is just f times, bracket comes later, tangent of phi s plus theta. So that gives us the p, right? But we're not really interested in p. If we go back here, we're interested in the moment. So we can say that is equal to m over r, which means if we want to get m, we'll get f times r times tangent of phi s plus theta. And that's what we're looking for. All right, so basically what this says is that if we know the radius of our shaft, we know the axial force that we want the screw to produce, and we know the thread angle, and we know the friction coefficient, then we can find what this moment is. All right, remember we talked about when we talked about wedges, we started talking about the idea of self-locking, and we also get self-locking screws. So maybe just as a definition we can say a screw is considered self-locking if theta is less than phi s. So that's a really handy, nice way to do it. Easy to find out. Much easier than for the wedges, which is quite involved. Now, if we want to loosen a screw, to loosen a self-locking screw, we can go through this whole system again, and what we'll find is that then m is equal to f times r times tangent of phi s, now minus theta. All right, so it's not all that different. We get almost the same equation, just plus versus minus. All right, so with that, we have figured out how to calculate the moment that we'd have to apply to a screw, to a square threaded screw, to create a certain axial force F.